we look at the classical simple harmonic oscillator. We learn the Hamiltonian. We know it has Hamiltonian, which is the kinetic energy plus the potential energy, right? And we know that in Hamiltonian, we have two independent variables. What are they? The generalized momentum and the generalized position, right? So in this particular case, P1 equal to P, Q1 equal to X, right? And so this is nothing special. You learn this even in Newtonian mechanics. You can come up with this, right? And we have a special constant omega naught, which is square root K over N, right? How do you quantize it? And this one, you just trust me. We don't have time or to go through this quantum mechanics. But the point is that we can promote the generalized coordinate and momentum, which are so-called conjugate variable of each other, or they call it canonical variables, right? Anyway, they have some very special meaning. We trust them. We promote it to an operator. So this operator, of course, in matrix quantum mechanics, in matrix form, right, Heisenberg form, it is a matrix, right? And it is special because these two does not commute with each other, right? And we remember the commutator means x hat times p hat minus p hat times x hat, right? It is equal to I h bar. If h bar is 0, then there's no quantum mechanics in this world, right? And because h bar is very small, it took us so long to discover quantum mechanics, right? And so it is very simple. Once you have the Hamiltonian of any classical system, you just plug in the canonical variables, the canonical conjugate variable, then you already get the quantum version of it. So why this is a quantum version, right? So what we say is, well, we can it turned out that you can create something called annihilation and creation operator. It's just an operator. It's just a linear combination of the x and p, right? You can create anything you want. It just turned out that this has a special meaning. And of course, your x and p can be a linear combination of these two operators also, which we will see later in the EM wave, right? And what's so special? We don't see it yet, just a mathematical exercise. But then if we create another operator defined as the A dagger and A, right? Then this one, for its eigenvector n, and with eigenvalue n, it has some special property that is related to this simple harmonic oscillator. Any operator, of course, I can write it as the operator times its eigenvector equals to eigenvalue times its eigenvector. It turned out this n has some special meaning. It represents the number of quanta of energy of this simple harmonic oscillator. For example, we can express the Hamiltonian we showed last time as h bar omega times n hat plus 1 over 2, right? It's just a long math, and after that you just trust it, right? We don't want to revisit that too much in the future. My goal is not to teach quantum mechanics, and we expect that we try to use minimal quantum mechanics to understand this class. But it just turned out that this n and h has this relationship. And it means they also have the same eigenvector. Then you actually can diagonalize them at the same time, right? But anyway, this n turned out to represent the number of quanta of energy that you have in the system. And with this definition, right, we know that the n equals to A dagger A. We prove that A, if you operate on n, you actually get n minus 1. So basically just saying that I have n units of energy, I apply the annihilation operator, it takes away 1 unit of the energy, okay? Or 1 unit of the fundamental particle, right? If I apply A dagger, it becomes n plus 1. It's just like I add one more particle or one more unit of energy to that system, right? And eventually have this equation, basically saying that how you create from vacuum, 0, all the way to n units of energy of n particles, right? So the math is actually not difficult. You just need to be careful about this commutation, right? For you, math should be easy. The difficult part is how to make sense out of this, and it will take long time. So that's why I would say, I just want you to understand, we start with the classical Hamiltonian and write it down in the right way with the correct variable, momentum and position. It can be generalized momentum, generalized position. And I make a mistake last time, as you remember, I put the velocity, right? Promote it with an operator. This operator is going to not, these two operators are not going to commute with each other. Then you will see the quantum effect. For example, if you remember where 1/2 comes from, it is due to the commutation of the A and A dagger, because it equals to 1. If it was 0, then this will be 0. And then when there's no n equal to 0, I don't have any energy. But now, because when this half, when n is not 0, I still have the vacuum energy, that the ground state energy that we cannot understand from classical perspective. And it's just telling us, in the vacuum, if you're quantizing the electromagnetic field, the vacuum, sometimes it will have the electric field, it will have a fluctuation of the electric field and magnetic field, which is going to affect your system, right? Just take this for granted, right? But I hope that you understand the math. You can follow. Okay, any questions? Okay, so a lot of math. So now we step back. Anyway, we just say in a simple harmonic oscillator, now actually it has an eigenstate, and from 0 to 1 to 2 to 3. So at different, it can have 0, 1, or 2 or units of energy, h bar omega, right? So I just want to spend some time to understand a little bit the matrix. So so we have some idea, right? Also practice the matrix. So for the operator, what do they look like? For example, what is the matrix form of A hat when we express, I need to say, in the lumbar eigenvector basis, right? If you want to express an operator in its matrix form, you need to tell me what basis you are using, right? So the easiest way, it is not difficult to find out. The matrix form is just a sandwich. If you remember the how do I say? How about, let me do row. This is difficult. The row and j column of a matrix, right? I think I did mention it earlier, but if you forgot or if I did not, how do you find it? Do you remember? It just sandwich the eigenvector and then the j eigenvector. Okay? Do you remember this? Okay? Now, what is this value? Now, A applied to J, what do you get? Huh?
Square root n J minus 1.
Thank you. He say it is square root J, I just call it J minus 1. I don't have n here. Sorry. Square root J, sorry, I said it wrong. Square root J minus 1, right? Because I remember that A applied to n equals to square root n minus 1. It is an annihilation operator, right? It take away one of them, right? And then square root J is a number. I can take it out. It becomes J minus 1, right? But these are the eigenbases. What are the possible values? They should be orthonormal to each other, right? So this one needs to be equals to square root j of delta I j minus 1. Only when I equal to j minus 1, I would get 1. Otherwise, it would be 0. Remember, we talk about orthonormal basis. Just like in the 3D, you have x hat, y hat, and z hat. X dot x is going to be 1, but x hat dot c hat or x hat dot y hat is going to be 0, right? They are orthonormal, right? Normalized to itself and then orthogonal to the others, right? So how would the matrix look like in this case? It means when I equals to j, what is this? When I equal to j, 0, right? Because j minus 1 is not equal to I, right? So I will have a 0 on the diagonal. Okay? Then when am I going to get 1? Right? Maybe I can write here. This equals to square root j when I equals to j minus 1. Is this okay? When I equal to j minus 1, then I get square root j, right? Otherwise, I get 0, right? So when I use square root j means the ith row equal to j minus 1. So you are going to get here, because this is ith row, there should be 1. Right? This is the first row. So actually, did I do something wrong? Yeah, so I should not, this one should be 0, I think. Then I may make some, yeah, did I make some? No, for the, here is the ith row, right? So this one should be, I should start with the first row. I even forgot. When I is 1, j is 2. I get square root 2, thank you. But I start with I equal to 0. Okay, thank you. So you are right. Thanks for saving me. So start with square root 1, not 0. Okay? And then this will be square root 2, square root 3. Keep going down. And then the rest is 0. So it's a shifted diagonal. I don't know how to call this, right? So it's not along the diagonal, but shifted by 1 row. Do you see this? Any questions? The next number. So this is the diagonal one, is all 0. Then you move to the right, you get square root 1. And then the rest is 0. Here start with 0, 0, when you reach diagonal, and then square root 2. Then the rest is 0. Okay? So this is A dagger. This is A, right? So similarly, how about the A dagger? It has this. Right? The ith row and jth column is defined by this. But then I know that this is going to be, if I apply to j, what do I get? A dagger? Do you remember? I get j plus 1 times I inner product with j plus 1, right? So again, this is similar to that one, but then it say that this equals to square root j plus 1 if I equals to j plus 1. Otherwise, it is 0. Is that okay? So with this, then the matrix is going to be, again on the diagonal, they are all 0. right? So when do I get non-zero number? I get non-zero number when I equal to j plus 1, right? So for example, I on the second row, which is I equal to 1, right? So I need to make this clear. Here is I equal to 0. So now here is I equal to 1. So when I equal to 1, then j equals to 0, correct? When I equal to 1, j equal to 0. Then it means at this 0 column, I have square root 1. Okay? So I will just keep writing this going down, right? So for the lowering operator, you have this shift to the top right. For the raising operator, you have the shift to the bottom left. So this means this 0, 0, 0, 0, 0, square root 1, 0, 0, 0, 0, 0, square root 2, 0, 0, 0, 0, like this. Maybe some of you cannot see this well, right? Why don't we look at a 3x3 case? It will be like this. 0, 0, 0, square root 1, 0, 0, 0, square root 2, 0. This is the 3x3 case. Do you see that? Diagonal is 0, and this shift by 1, square root 1, square root 2. Any questions? Right, it's a little bit messy. I call this 1. This is 2. And then I want to talk about 3. Yeah. No, first row is I equal to 0. We start from 0. Because the eigenvector have 0, 1, 2, 3. For n, right, n goes from 0 here. Do you see this? 0, 1, 2, 3. This is the basis state, right? So the basis state of all the matrix go from 0, 1, 2, 3. Okay, like this. If you don't see it, this is like 0, 1, 2, and you keep going. Okay, so the first row is 0. First column is 0. Okay. Now, then how about x? Now, x is just equals to h bar divided by 2m omega a plus a dagger, which I did not mention last time, but I gave you in the review, just the addition of them, right? So if you try to write the matrix form in the n eigenbases, then this becomes what? I just add them together, right? So this is diagonal. And then I have square root 1, square root 2, square root 3, square root 4. This is due to a. But a plus a dagger, right? So I also have square root 1, square root 2, square root 3. And you keep going, right? If I just, I should not write this then. Yeah, if I try to fill it up, it will be something like this. Right? Do you see that? So I have two, not really diagonal, right? 2, 45 degree 9. So that is the matrix of this one, right? And then maybe you try the P yourself. We can maybe put in the homework. So this is just a review, but it's very important to understand in simple harmonic oscillator, we often operate on this eigenvector of the number operator basis. Okay, any questions? Okay. Now, so we already, you see we did not solve the Schrodinger equation actually, did we? I don't think we have, right? Oh, we did, because we do H psi equal H times the eigenvector equal to eigenenergy times the eigenvector. Of course, we did that. But how is this in the real space? We're talking about in the matrix form, right? How is this in the real space? Now here I want to show you a derivation, but you just take it for granted, because again, we don't want to go to quantum mechanics. That is not the purpose. But let's think about this, right? First of all, we know that if I apply a lowering operator to 0, it will give me nothing, 0. It's not 0 state, it just destroys everything. No, it's no longer a cat, okay? Or you can say, yeah, it becomes 0 times cat, then anything times the cat is 0, okay? It just, everything is gone. Now, then, naturally, if I add the eigenvector of position to the left, look at this. X is the eigenvector of position, right? We talk about position eigenvector. You apply the position operator to the position eigenvector, you get the location, right? Apply it to 0.2, then I get 0.2, right? Apply this one to A, right? Just apply this one to the right. What should I get? What should I get? 0, yeah, because this is 0. Okay, but I will further show that, but not further. What is A? I can talk about A. I just show you what A is, right? I need to go to the beginning. A is equal to this guy. Okay, so I'm going to copy the whole thing here. It becomes X, maybe I put a hat here would be better. So you know it is operator. It is X hat plus I P hat divided by M omega, the whole thing applied to 0, right? And I ignore this term in front of it because it is 0, so it will be removed, right? A hat equal to constant times X hat plus I P hat divided by M omega, right? So that's what I did. I substitute A hat with this guy, but I just ignore the constant term because it is 0. It's going to get cancelled, so I just ignore it. But in case some of you feel uncomfortable later, let me still add it, but it will be gone. Is this okay? Right? So basically, this tells me that X hat plus I P hat divided by M omega 0 equal to 0. Okay? Now, this is a two operator. I can do it separately. What is X hat applied to X? X hat, I'm talking about this. X hat applied to X. What is this? XX, right? Because X is the eigenvector of X. X hat, right? The location eigenvector. So you get this. It becomes a number. Okay? Now, if I also apply zero to the right, then what do I get? I get X times X0. Right. Now, what is the meaning of this one? What is the meaning of X0 inner product? It's projecting the eigenstate of the number operator 0. This is one of the eigenstate. It means the ground state of the number operator. It's just like spin, the states of spinning up, states of spinning down. Now this is the state of zero, of the ground state of the simple harmonic oscillator with n equal to 0. But I do the inner product and project it to the real space eigenvector. So basically, I'm asking for when you have a 0 state, you are at the ground state, how much component you have at x equal to 0, at x equal to 1, x equal to 1.5, x equal to 1.6, at x equal to x. Do you get what I mean? Basically, this one is the wave function of n equal to 0 at x. That is the meaning of this projection. Right? You have an eigenstate, and I try to understand how is it how it distributes in the real space, right? So this is what we want to solve. This is psi of n equal to 0, okay?
Can you explain the connection again with the wave function? Because you jumped.
Yeah.
Can you describe it in this diagram like this line psi 0?
Yeah. Is this one. So you want me to explain one more time, right? We have been talking about quantum mechanics. Everything is represented in a state. You call it a state. For example, I say this is the state for n equal to 0. That's it. But how does it perform? How does it exist in the real space? I did not tell you, right? I say this is ground state. Right? Just like in the spin matrix, I say this is spin up. If I do not understand what is spin up, I only understand what is spin left, spin right. Then I want you to tell me, what is the component of spin up in my spin left and spin right basis? And then you say it will be 1 over square root 2 spin left and 1 over square root 2 spin right. Okay, but how do I get that? I'm going to find the component by using spin up and project it to the plus basis. That gives me the component, and then project to the minus basis. That gives me the component. Then I know that I have this much of component on the plus, this much component on the minus. Same token here. You tell me that you have a state that is at the ground state. So, yeah, ground state, fine. The ground state of your system is the eigenstate of your number operator. You form your own space, fine. But I want you to tell me, how does it appear in the real space? Then what do? You project this ground state here to the eigenstate of the coordinate. The eigenstate of coordinate is this point in the space, x equal to 1.1, x equal to pi, x equal to 1.25. You project to each of this point and tell me that, oh, it has this component at this location. It had this component in New York, and it had this component in San Francisco. I give all the location. Then I construct the wave function of this state. Okay, any questions? This is confusing. I do not require you to fully understand because we are not going to use this type of operation in our exam or maybe homework. We can try that, but you can ask me. But you just trust me, right? I hope you can go through this. This is the connection between our usual wave function, real space wave function, to the matrix mechanics. Okay? So that is how we get the component. Then we have another one. How about this term? x I p hat divided by m omega 0. Now this one, we are not going to go through the derivation, but you trust me or read Sakura's book or other quantum mechanics book, p in the real space, it can replace by negative I h bar partial x, right? Because short summary is that the momentum is the generator for translation, and you can prove in that way, okay? But it turned out to be that, okay? So, I mean, in some classes, we just take this as granted, and then you do substitution. So there's no point for us to keep going deeper, right? But because of this one is equal to, because you have I, right? Negative I times I becomes plus, correct? So this one becomes x 0, which is a number, and replace it by h bar partial x. Am I right? I think so, right? So eventually I get this equation, which is x plus h bar partial x, the whole thing, on x 0 equal to 0. I do miss the m divided omega, no wonder. I still have m divided by omega. No I, this already have an I times negative I becomes 1. Because P, only P becomes this, right? Then this whole thing need to multiply by I divided by m omega. Yeah, good point, right? And if you are still not familiar with this x minus x, x inner product with 0, no, what do I do here? Did I miss the... I think I did something wrong with the x. Okay, I think that's right. Should be right. Yeah, my cheat sheet has problem, I guess. No, so but anyway, you just solve it, right? Then you will find this. Just solve it. And we are not going to solve it. You don't need to solve it. The whole slide, if you want to study, is good if you go deep. But otherwise, I just want you to know that if you solve it, you get this answer. X naught is just a constant, which I did not give you here. I forgot to copy, but it really doesn't matter. You solve it, you find that it is a Gaussian pulse, a Gaussian shape. Means that at ground state, you actually have a wave function that you are spreading everywhere. This one shows you the potential energy, 1 over 2 kx squared. Classically, I mean, if you follow this, classically, this guy, you should not have any particle that will penetrate here because it has, your energy is at here, right? When n equals 0, you have the fundamental, this ground state energy, vacuum energy, which h bar omega divided by 2, right? If you have one more unit of energy, you have h bar omega plus h bar omega divided by 2. Each of them keep going up. Each of them is h bar omega, right? Following, do you remember following the E n equals to h bar omega times n plus 1 over 2, right? This is the energy of your system when you have n number of particles. or n number of quanta of energy, right? But the wave function, the probability that you will find this particle is that it has this type of tunneling into the forbidden region. Because classically, if you have energy here, you should have 0 probability to find your particle here, right? So here signify the quantum mechanics. But however, you look at all these eigenstates, none of this is related to what you feel classically. Isn't that we're talking about a harmonic oscillator vibrating back and forth on the x coordinate? It should go like this, right? If you try to find the average of the energy, the position, try to find the average of the location, you find that it's always at 0. But my simple harmonic oscillator is oscillating. So this state corresponds to what I'm observing classically, right? Because this is called corresponding principle. When you go to the limit, your quantum mechanic treatment should be reduced to a classical treatment. But none of them correspond to what we have, okay? And these are called the Fock state. They are the states that purely quantum. And that is not what we observe classically. What we observe classically should be something like this. The wave package should oscillate back and forth on the x-axis, right? And what are these states? These are called the coherent state. This is something very close to the classical. So when you see the particle oscillating back and forth, right, classically, it's actually a coherent state. And this coherent state must be a linear combination of the Fock state, okay? So coherent state, first of all, it turned out to be the eigenvector of the annihilation operator, right? We can try to prove this later, but the important thing is that it does form, they call it over-compete, more than required basis, right? When we say complete basis, basis states they can span the whole space, right? But this guy has more than what is required to span the whole space. So this is over-complete. And it is also lot of normal. Right, so this is not a good basis for us to work on. However, it corresponds to the classical state. So how does it look like? So I will just say that it is the eigenvector of A. Then, of course, A operates on this coherent state alpha must be equal to alpha times the eigenvector, right? The A is the annihilation operator. When we say something is the eigenvector of the operator, then it must be equals to a number times that eigenvector, right? And that number is the eigenvalue. I call it alpha. That is okay, right? And it turns out to be what? E to the power -1/2 alpha square summation n equals 0 to infinity alpha n divided by square root n factorial times n. I know this is very long, but you want to appreciate it. This corresponds to a classical state. Right? Very close, resemble, I should say, it resembles a classical state. Let's look at it. It is a linear combination of n. What is n again? Energy eigenbasis, or the number operator eigenbasis, yeah? N, right? N equals 0, 1, 2, 3. How much? This is the n. Each of these correspond to one n. N equals 0, n equals 1, right? And each of them, as we just discovered, has nothing to do with the classical, because look at the ground state, the mean is Gaussian, the mean is at 0, it's not oscillating, right? But we form a linear combination of n from 0 to infinity. but it is scaled by the coefficient of alpha to the power n and also square root n factorial, right? And alpha is a parameter. And then normalize it. We need to normalize this guy. Maybe we can try homework with this coefficient. Then, not normalize, sorry. This is not to normalize. This is to make that so that you fulfill this eigenvalue equation. Okay? Then we create a state. So this state is a linear combination of the the eigenvector of the Hamiltonian, as he said, right? So it's a linear combination. And if you do this linear combination, right, you see this wave package is oscillating back and forth like the ball you see in a simple harmonic oscillator. Now this, why I want to discuss this later, we might not do this in the class, but if you read paper, you will see they always talk about the Fock State, the Coherence State. Then I hope you understand what it is. Okay? Yeah.
Shouldn't there, well, where's X in there?
There's no X because I'm representing it as a state. If I want to project to X, I need to repeat this process. Project this to A. So this one, this guy now is actually X, project this one to here as a function of time. So here we did not put in the time, right? We only put in the package. Yeah. But because, yeah. Okay.
Yeah, the wave function is only X, there's no time.
No, so here you need to put, because for each of them, right, here we assume not time dependence, but each of the n, it has different omega. That is how you oscillate. So each of them, you are going to have different e to the power negative I omega times n plus half. I think I need to check. It will oscillate each of the wave, right? Because this is the state itself, right? And then you add them constructively and destructively. And that's how you get this one. Okay. Okay. So we are done. So what did we learn so far about quantization of simple harmonic oscillator? Very messy, right? But basically, I hope at least you know we start with classical Hamiltonian. We do the promotion to the operator. And then if you choose the correct conjugation, right, you will be able to have this commutator issue. They do not commute. That introduce the quantization. And the rest is just, then we introduce the raising and lowering operator. And now you understand, at least for a simple harmonic oscillator, you actually have the raising operator to inject one quantum of energy, or the lowering operator, which is the annihilation operator, right? So I did not say that. Creation operator, you can call it raising operator sometimes, right? And annihilation operator, you can say lowering operator, right? So you keep adding different things. And just watch out for what basis we are talking about, whether it's the eigenenergy basis or the other basis. Okay, yeah, question?
So why this is psi square?
Because it's trying to plot the probability. What is the probability of finding a particle at a certain location? Is psi square, right?
Okay, so it's
Yeah, for probability. So can we do the same thing for electromagnetic field? Now, the slide's going to show you very complicated, do not worry. But I just want to tell you that you see that we do the same thing as we did for simple harmonic oscillator, because the